So this is Artificial Intelligence and Games, a two-way street. This is the updated version of a talk I gave at MAGFest 2022 before the release of ChatGPT. A lot about AI science has not changed. A lot has. One thing that has not changed is video games need AI. And like you saw in the little blurb in Guidebook, AI means something specific to gamers that it might not mean to like researchers or investors or people on the news. Gamers have been talking about AI since like 1955, before it was like popular or profitable. So this talk, to start with, in accordance with the Navy Education and Training Manual, I have to give you what's called the What's in It for Me. It used to be called the What's in It for You, but that was pronounced waifu, and you nerds ruined that. So now we call it the WIFM, which is fun to say, so it's not like a loss, whatever. Can I make this bigger? Yeah, okay. All right, so every gamer has dealt with AI. Every designer has had to deal with designing an AI. AI research has contributed a lot to games. A lot of the things that you do to code an AI in a video game comes from classical computer science. And you just kind of wrench those algorithms into place to match the needs that you have for your game. But nowadays, games are contributing to research to the point where it's a closed loop. Games contribute to research, research contributes to games, and it all kind of matches into itself. The last 5 or 10 years of AI research have been explosive in a couple of ways. AI has changed in the last 10 years, 15 years now, I guess, from hand-coded to machine-learned in cutting-edge research spaces. We'll see in a little bit why that doesn't really make its way into game design as much. But we'll give you a sense of what the research challenges and milestones are. So if you're interested in why a computer game plays the AI the way it does, or if you're a developer who wants to use AI, this will tell you like how we got to where we are. I'll give you some advice if you're a gamer, if you're a dev, or if you're an artist about what AI means for you, how you can use AI, what concerns you have about AI, and we can talk about some of those too. Another panel that I've given in the past is like helping people write narratives with AI in it. So if you have some question like, I'm writing a story where AI tries to do this, is this possible? You can throw that in there too, and if we have time, we'll get to it. So here's our agenda. I'm going to tell you who I am and why you should care what I have to say. We'll try to define AI. We will fail. I'll give you some examples in games. We'll talk about some of the application challenges and examples of artificial intelligence, some of the critical milestones in research that have made AI the popular thing. AI research has been around since the 50s, but nobody took it seriously until like 2012. Why? And like I said, we'll give you some advice based on whatever your relationship to games is. So who am I and why should you listen to me? My name is Chris Dailey. I have a degree in computer science from the US Naval Academy in 2008, and I finished graduate training in information and data science at the UC Berkeley in 2016. And until a couple of months ago, I was the head of artificial intelligence at Electronic Warfare Associates. We do stuff like smart radars and jammers and like intelligent counter-drone technology, stuff like that. But I left to start my own thing. But it doesn't have any name recognition, so I'm not going to tell you that. My gamer creds are that I didn't think Lion King for the Sega Genesis was actually that hard. Yeah. I was a nationally competitive Soul Calibur 2 player, although the results of today's Soul Calibur 2 tournament have shown me that I #don't still got it. I have not played the game since 2003, and it shows, although I can still bang out a Summon Suffering in a competitive environment, so don't sleep on me. And my Steam library has had a scroll bar since 2005. All right, so what is artificial intelligence? Here's the thing, we don't know. Nobody knows. A common exercise in your first year of computer science undergraduate is the professor will stand in front of you and say, what is a computer? And you will take the whole session to do your best to define a computer in a way that includes all the things that you think of when you think of computer, but does not include humans. It's really, really hard to the point that it's impossible to define what a computer is. AI is kind of the same way, especially nowadays when it does stuff now that it didn't used to be able to do, and it does stuff now that nothing used to be able to do. So it means different things to different people. The way we're going to define it is AI is a system that accepts input and makes decisions, potentially taking the related actions based on that decision that would otherwise be made or taken by a human. So if you're playing an AI in a fighting game, usually you have 2 human players, but if you only have 1, you're playing against like the AI. So that's an AI. But lots of stuff falls into this category. There are the brightness sensor on your phone. It reads how bright the room is and modifies the brightness of your phone. The thermostat in your home, the cruise control on your car. It reads how fast your car is going and opens or closes the throttle based on that. That's a decision that you, a human, would otherwise make, but a machine is doing it. So I call that AI. But it's not just computers. The picture here is what's called the centrifugal governor from the original steam design published and patented by James Watt. The faster the engine spins, the faster this governor spins, and these 2 stalks with brass balls on them will raise out. And the more they raise out, the more energy it takes to spin them, so it will naturally slow the spinning down, and the speed of that spinning controls how open a valve is. So the faster the engine spins, the more the stalks lean out, and the more the throttle closes. So it keeps the engine spinning within a certain range. That's AI too, and that was in like the 1850s or something. But some initial decisions must be made even if you're going to like machine learn an AI. Like it's not, as we'll see, it's not just you turn the AI on and it learns stuff. You still have to make some initial decisions. In this case, like how high up the stalks you set the brass balls, how heavy you make the brass balls, those are decisions that you make that will change the range in which that steam engine runs. This was clearly not machine learned. This was designed by a human. But it's artificial intelligence. So it's not machine learning, but it is artificial intelligence. These things are different. Machine learning is different from artificial intelligence. They're spoken in the same breath nowadays because all the recent advances in artificial intelligence have come from machine learning. But they are not one and the same thing. So we'll get to machine learning in AI, but please keep in mind that AI and machine learning are different things. This nuance gets lost in the news cycle as people talk about data centers and water usage and copyright laws and like salacious artificial pornography. These are different things. For the purposes of this talk, we'll talk about AI in the video game sense, competitive. So either the environment of the game has to behave in a certain way, or you're playing an opponent in a game, and that's the AI that we'll talk about. We will discuss generative AI a little bit at the end, but it's not going to be the focus of the talk. All right, so why is game AI hard? If you've ever developed a game, you can use commercial or free assets online for like icons and art and sprites and BGM and sound effects and stuff. You can use open source game engines like Unity or Godot or whatever. It's pretty easy to come up to speed as a hobbyist coder to learn like the basics of programming, and most widely used game engines have really good tutorial libraries out there. So you can learn how to do all of that stuff. It's much harder to learn how to code an AI because there's a bunch of reasons. But one is that coding an AI is very different from coding like a set of instructions to follow, or like create a window with a button. When the button is clicked, do this. It's a lot. There aren't like libraries like tkinter or like Qt or whatever that you can just drag and drop. Like you kind of have to know what you're doing. The support is getting better. But even if you sit down and try to work on it, you'll discover that it's hard and there aren't any really easy questions to it. It feels like it shouldn't be hard. Theoretically, this is provable. No matter how complicated the system you want to learn is, it can be arbitrarily represented with an unbounded list of if-then statements. No matter how huge your game is, no matter how complicated it is, there's only a certain set of states that the game can be in. And for each of those states, you want the AI to take a certain action or some set of actions or an action drawn from a distribution of possible actions. So you really could just list every possible state your game could be in and write an if-then statement for it. If you're in this state, take this action. This is possible with blackjack. You have a list of depending on how you want to count it, between 34 and 70 possible opening hands, and you can statistically show what the best actions are to take for each of those opening hands. The game is set up in casinos so that even if you play according to this, you'll still on average lose. You can kind of cheat this by like counting cards and literally cheating, but you get kicked out of casinos for doing that for that exact reason. So a game like blackjack, it's possible to code an AI just with if-then statements. But that's not possible for most of the games that we like to play. Has anybody played Slay the Spire? Slay the Spire is a roguelike game that you play over and over, and you have a hand of cards, which is start at the beginning of the game, is drawn from a standardized deck, but you can change your deck over the course of the play. Every card that you have in your hand, you can have up to 10, and so if your starting deck has 30 cards, that's 30 choose 10 possible states just with your opening hand. You can also collect relics in the game, and there are 127 different relics. And so if you collect 10 relics over the course of the game, that's 127 choose 10 different possibilities. And some of those relics, like you can see the third from the left, the pen nib has a state. The pen nib is on counter 1. It counts up to 10. On your 10th hand, or on your 10th play, you deal double damage on that play. So the optimum strategy will depend on what cards are in your hand, which is a gigantic state space, what relics you have or don't have, which is a gigantic state space. Some of those relics are stateful, and that is not to mention the fact that there are hundreds of different enemies. You could have different amounts of hit points, different amounts of maximum hit points. The number of states in Slay the Spire is conservatively in the quadrillions. So like, you're not going to sit down and write quadrillions of if-then statements for every possible state in the game. So clearly you can't just do if-then statements, even though it's theoretically possible. For some games it is, but for most games that matter, it is not. Another reason that game AI is hard is that games can have a complex game tree. So the board game Go is like a little bit more popular now than it used to be because of its role in like computational, artificial intelligence and things like that. The first stone you play on the board, you play stones on the intersections. Where's my mouse? You play stones on the intersections, and if you place a stone here on what's called the 3-3 point, that's one viable way to play. If your first move is one intersection north on the 3-4 point, the game will be wildly different. And if you play your first stone on the 4-4 point, the game will be unrecognizably different. These tiny initial changes result in such a gigantically different game down the line because the game has a large game tree. If you're not used to thinking about what a game tree looks like, we can look at tic-tac-toe. This is the complete game tree for the first 3 possible game states, so the first 2 possible moves. You start out with a blank board. You have 3 possible moves to begin with. You can play in the corner, you can play in the center, you can play on the side. You might think there are more, but they are equivalent to these just by rotating the board. You can use rotational symmetry to decrease the practical state space of the game. And then you can see what the potential follow-up moves are. Tic-tac-toe is a small enough game that you can do if-then statements for all of these. Like you can exhaust the entire game tree and see all ways that the game can possibly go and decide what action your AI should take in those states. But that's tic-tac-toe. Like not a ton of people are like scrolling on Steam for the tic-tac-toe tag to find out what the hottest tic-tac-toe content is. So this is not where people want to like innovate with games. Typically, if you do make a tic-tac-toe game, please let me know. I would love to play it. That would be so funny. Even apparently simple games have a surprisingly complicated game tree. The game checkers, which is like one of the quintessential games that you use to describe somebody playing a simple game, like, oh, this guy's playing 5D chess and you're playing checkers. The implication is that checkers is pretty simple, and it is compared to 5D chess. But even checkers has a gigantic game tree. Researchers, I think in Toronto, in the 1980s, mid-1980s, said, we're going to play every game of chess. Or every game of checkers. We're going to write a computer program that just does every possible move. And they finished in 2014. They just kept adding more and more and more compute power to it and computing faster and faster and faster, and it took them decades to play every possible game of chess, or checkers. So now checkers is solved. You can see at any board state, without any probability at all, with complete certainty, who is winning, who could possibly win, who can force a win, who can force a tie, etc. And that's just checkers. So it should go without saying that a game like chess or Go has a gigantic game tree. It's really hard to compute precisely how many states there are in a game tree, but even making every conservative guess you can, there are more possible games of Go than there are atoms in the observable universe. So even if you use the entire universe to store information, with every atom being a 1 or a 0 based on, I don't know, the spin of electrons or something, you simply could not even enumerate, much less store, all the possible games of Go. So clearly, the if-then statements are out. One of the reasons is this complex game tree. So how do you code an AI? Well, some of the most direct answers are math and computer science. We talked about the complex game tree. If you play a game like Total War Rome 2 or Rome 2 Total War, I always forget the order, you have a bunch of different cities all over the map, and you have options of what to build in each of those cities at what turn, and you have different like government types, so you can see how explosively the game state and the game tree grows, right? There are certainly more possible games of Rome 2 Total War than there are games of Go, and we've already established that Go is unmanageably huge. So you can't enumerate all of them. But what you can do is you can try to reduce the size of that tree. You can use what are called pruning techniques, where you chop out, if you think of it as a literal tree, you're literally chopping branches off of the tree to make it smaller. And you can usually make it orders of magnitude smaller by using tricks like min-max trees, alpha-beta pruning, a technique that we'll talk a little bit later called Monte Carlo tree search, where you follow some paths down the tree, and then you back up and try other paths, and which paths you choose is based on some almost literal roll of the die. And you can reduce the size of the game tree by orders of magnitude. The problem is you're taking it from like 10 to the 124th down to 10 to the 121st, which is still a gigantic decrease in the state space, unimaginably huge decrease in the size of the state space, but you are still left with an even more unimaginably huge game state left over. So you have to find, clearly you'll have to find some way to do more than just prune the tree, although we'll find out later that you don't have to do much more. You can use traditional algorithms from computer science. This is a visualization from the game Factorio. Factorio is it's kind of like cocaine but in a video game. And if you just got fired, Factorio is a great game. No one else should play Factorio because you will disappear into your little compute hole, and your family will wonder what happened to you. But the people who have you on their Steam friends list will say, oh, it's Factorio. This is a visualization of how the biters, the enemies in the game, find a path from where they start to where they're trying to get. Maybe you've never thought about this. If you're playing like StarCraft and you select some units and you right-click somewhere, they go there. But they don't go in a straight line. They go around the stuff that's in the way. How do they decide where to go? There's a whole bunch of different paths they can take. Why do they choose that path? How did they find that path? When you click, it happens immediately. So they must find a path pretty quickly, certainly much faster than you could. Like if you looked at the map, you would have to be like, all right, so I'll go here and here. Oh, no, I can't. That's a dead end, so I have to back out and go here. Well, they actually do that. What you're seeing here is a visualization of what's called the A-star algorithm. This is a classical computer science algorithm from like the 60s that finds a path through weighted directed graphs. So if you imagine every discretized square of space on the map is connected and adjacent, except for some that are not. You see there's a cliff in the way, right? So the squares on one side of the cliff are not connected to the squares on the other side of the cliff. That's nodes and edges. That's a graph in the computer science sense. And so really all you're doing is converting the map to a graph, picking two nodes, and finding the shortest path through them. A-star is an algorithm to do that, and this is slowed down so that you can see it, but like it runs much faster. In the original StarCraft, pro players figured out exactly how the algorithm worked, and they found lots of little tricks to exploit it. Like one of the things you could do is if you watch pro players, I don't know if this works in Soul Calibur 2, it's the greatest game ever made. We could talk about Soul Calibur 2 if you want. But in StarCraft 2, I don't know if this works, but in the original StarCraft, if you right-click to send units somewhere, they'll follow a certain path, but if they're on the way and you right-click the same spot, sometimes they'll change their path, even if nothing else in the game state has changed. Why wouldn't they have just gone on that first path if it was the optimal path, right? It has to do with the nature of how it gets computed, and pros found out that you can get your units to take a more efficient path if you just sit there and you keep clicking over and over and over so they recompute their path along the way. That's actually what started the APM craze. Like the major, if you're not familiar with this, actions per minute is like one of the ways that pro players like measure their proficiency. It's insane how like many actions per minute pro players are taking, and a lot of them are just like clicking to get their units to take the most efficient path that they can, because microseconds count in like pro play, so they care about that. In fact, until recently, if you looked at the AI library for the Unity game engine, if you looked in the AI section of the game engine documentation, you would find that it only consists of like pathfinding algorithms. So for a long time, this pathfinding is what AI meant in game design. It's a little bit different now. So if you have hard questions like how do I get my enemies to go from one space to the other without just running into a cliff and stopping, computer science has a whole pile of algorithms that you can use, not just for navigation, but for all kinds of other stuff. Some problems in games are what are called NP-hard or NP-complete, which means you can get approximate solutions to them, but there's no fast way to find the best solution to them. And if you want to get a degree in computer science, you can learn about all of that, but there's plenty of posts on game dev forums that are like, here's what this algorithm does, here's how you can use it, here's what this algorithm does, here's how you can use it. So you don't need to go to college and study all this computer science stuff just to use it in your game. Here's another great way to code an AI. You can cheat. If you're familiar with the game Civ 6, you know that at the end of every game you get this delightful screen where you can go through charts that show you the value of various scalars throughout the game, like number of combats, units killed, how many people are following your religion, how many cities you founded, whatever. One of the things you can look at is how much gold is in each player's treasury. This is the chart from the end of a game of Civ 6 that I played years and years ago. But this was the first time I noticed this. If you look, there are huge spikes followed by huge drops in some of the charts. What's happening is that when a computer faction has war declared on them by a human opponent, the game engine gifts them a huge pile of gold that they immediately spend on military units. And the reason for that is because it's actually really hard to code an AI that is smart enough to watch your civilization to see that you're building up units, what kind of units they are, how many there are, how close they are. And so when should the AI start building walls? Should the AI build cavalry or spearmen or maybe archers or whatever? That's really hard. You could definitely do it, but it would take a lot of time because that's not like what people typically get into game development for. They want to like play the game and have fun, and this is like behind the scenes, it's under the hood. Some people like that, but most people as like hobbyists or amateur or indie coders do not. And so you could be forgiven as a game developer for being like, well, what I could do is take a year and read all of these machine learning papers and train an artificial intelligence to learn how to do this, or in an hour, I could just write code that gives it gold. And I played Civ for 2 years before noticing this. So you have to be either really interested and inquisitive or really good at the game to notice that the game is cheating. So like, I use the word cheating because it is by the rules of the game, but from a game developer's perspective, I don't think this is cheating because you, the player, still get a good experience. And if you are fooled into believing that the AI is like playing in a human way, if it gives you a fun experience, I don't think that's cheating from a game developer's perspective, and especially if you're an indie developer who can't like call up the AI department and be like, hey, can I get 600 engineer hours over the next 2 weeks to help code an AI? If you work for Blizzard, maybe you can do that. If you're like Lucas Pope or Toby Fox or one of you who is like working on your own indie game, you don't have anywhere close to that kind of access. And this is so much easier. So I think this is a defensible game design strategy, and you're actually used to seeing it. It comes up a lot. I'll give you an example here. I'll say used to be, a very good Soul Calibur 2 player, very good. And like people on fighting game forums study their game like it's college. One of the things that every competitive fighting game aficionado knows is frame data. If you're playing a fighting game, if you, in Soul Calibur 2, for example, if you swing like a vertical attack at somebody and they block, both of you will be animation locked for a certain number of frames. The game ostensibly runs at 60 frames per second. And whoever's doing the blocking will regain control of their character 7 frames earlier than whoever was doing the attacking. So if both players are mashing the attack button, if there's less than a 7-frame difference between the hitbox of that move coming out, the person who's blocking will always interrupt and deal damage to the attacker. So the game enforces this normal tempo of a push and pull, your turn, my turn, that kind of thing. And competitive players memorize the frame differences for different moves. And so that's how you build up your strings, that's how you build up your strategy. So when you watch very competitive players play a fighting game, sometimes you will see like a pattern of moves, and that's because both players know what the optimal play is for that string of moves because they both know the frame data. They're like, I know I can't push the attack here. I have to block 3 times before I get a frame advantage, and so like the decision doesn't come, do I block during this string? You're going to block during that string. The trick is, what mind games do I play when I get the frame advantage? Do I delay? Do I fake? Do I attack immediately? So what we're going to see here is a video game from the original Street Fighter II in the arcade, and what we'll see is that it plays differently versus the computer versus a human. So if you watch here, Ryu lands a high attack, a low attack, and then throws out a low kick, but it doesn't hit Chun-Li. Chun-Li is able to hit him. You can see it again in slow motion, throws out the low attack. Here, Chun-Li becomes invincible. So she ignores his low attack and hits him with the kick that would, by all rights, be interrupted. So you can watch the same thing with the human player. I'm sure you can guess what happens. She does get interrupted. So if you compare the exact same 2 moves versus a human versus a computer, the computer gets some iframes, some invincibility frames, and so the frame data is invalid. It cheats. Game developers have been doing this for decades. This is nothing new. And unless you're a very good player of that game, you will never notice that. So when I say this is like cheating, I mean it's cheating in the video game sense, not the video game development sense. I think this is a perfectly sensible way to code an AI because it's very, very hard. All right, so let's take a break for a JoJo pose. And let's look at some questions. All right. So is something like Halo Smart AI possible? That is an AI that is made by copying the neural patterns of living people and incorporating it into its systems and UI. Would it degrade like it does in Halo? So the answers are yes and yes. So we'll take like 10 minutes to answer some questions here. The technology that makes modern machine learning possible are called neural networks. In fact, they're called deep neural networks, which have been around since if you want to call the perceptron a neural network, that's like 1953, and people didn't make them deep, that is, add more layers to them, until like the 70s. But until the early 2010s, they were just so slow to train and so slow to learn, and as we discovered in the 2010s, there wasn't enough training data, so they didn't really work. And so people didn't really take it seriously. But many researchers, a few researchers, stuck with researching neural networks, and they're given that name because they're inspired by the structure of your brain. Your brain is like synapses connected by axons, and the way it works is a bunch of different synapses will drive a voltage into the axons, and if it meets a threshold, the axon will pass that voltage on to the synapses it is connected to. So it is a neural network. It is a network of neural nodes. If you turn that into math, it's actually pretty simple math to mimic that. And so the whole idea of neural networks is that they mimic the structure of your brain. They don't match the structure of your brain. We have deviated significantly now from the way that we know the brain is structured to how modern neural networks are structured. And we also know that because of the way the brain is structured, that has connections that will form a cycle, so you can follow axions and get back to the original neuron where you started. The algorithm that we use to train neural networks called backpropagation does not work on the brain. So we know the brain doesn't learn the way that we train neural networks, but that's where the inspiration comes from. All you need is training data, and one of the reasons that image and music and text generation has been the explosive area of AI progress is because there's a huge amount of data available for that. And it's frustrating because it's like, well, why don't you train machines to like mine coal instead of like paint paintings? Painting paintings is fun. Let humans do that. Mining coal is not fun. Make the robots do that. And the answer is there's really not any training data of how to mine coal. That is changing. If you're seeing out there the humanoid robots that people are like pushing to like be your in-home assistants, do not buy those, first of all. I don't know how much sci-fi you have to read to convince yourself, it's not much, that that's a bad idea. But especially universities and particularly very well funded research organizations like DeepMind and OpenAI are like hiring people to have sensors attached to them and do their tasks. To do things like wash dishes, to do things like, not mine, what do you do to wheat? Farm scythe to reap wheat, right? And the more you do that, the more training data you have, the easier it is to learn to do these things. So you really could do that. One of the things, the second part of that question, would it degrade like it does in Halo? The answer is also yes. So models suffer from what's called staleness or decay. The data that you train your model on is necessarily finite. Like you have to take an amount of data, you can add more data to it, but you can't collect data from the future. So you only have data that represents things that have happened in the real world, right? But the real world changes. If you train a neural network to learn how to drive, and then somebody invents floating cars are going to drive differently than the cars that you have trained it to like recognize. So your model will have decayed. Even though the model stays the same, the process it's trying to model has changed. So relative to what you want to model, your model has decayed. So model decay is more or less inevitable. So yes, it is possible. Yes, it could degrade like it does in Halo. What is the absolutely most stupid and useless fact you can give in regards to games-related AI? My favorite is that Demis Hassabis, who is the CEO of DeepMind, which is a company that we'll talk about more later, his first job out of college was a programmer for the game Black and White. Has anybody played that from back in the day? There was a little pet that you had in the game, and if it was doing something you didn't like, you could slap it. And as you played, the more you slapped it, the less it would do that thing. That was machine learning. It was using what we now call reinforcement learning, which is the technology that Demis Hassabis based his whole company on that we'll come back to later. So I don't know if it's stupid. It's certainly useless. But like the seeds for AI have been sown for a long time. Let's see. All right, we'll do a couple more. Is Gabe Newell a benevolent AI construct pretending to be human? I hope so. I would like him to live forever. If he could escape the bonds of biological limitations and live forever, then God bless our Lord and Savior Gabe N, because he's one of the only billionaires out there who acts like a human, even if he's an AI. So my answer is I hope so. What is present? What if I click present? Does that like bring it up on the screen? Yeah, that's funny. Thank you, Charles Ford. Can you pose again? Yes, there is another JoJo pose break later in the... Is Gen AI the next big thing for NPCs, or is there another type of AI machine learning that isn't very well known yet that you think makes things go to level, especially with NPC interaction? Yes. We will talk about reinforcement learning later. All of the big progress leaps that have been made, like LLMs, ChatGPT, multimodal generative AI, those all use a kind of machine learning called supervised learning. We'll talk about the difference between supervised and reinforcement learning later. I personally, I don't know what your personal beliefs are, I find very, very distasteful the move towards machine-generated art being used in video games. We'll talk about some solutions to that later. So I don't like that. I don't like the fact that that's what people think of now when they hear AI, because there's so much good, useful stuff, what I would call like meat and potatoes machine learning, that's like the real useful stuff that you can do, and it's kind of guilty by association. Like if you say, I was worried people would protest this talk, because there are a lot of artists who are like, I think justifiably, violently opposed to machine-generated art. For practical reasons, for ethical reasons, for legal reasons. And I think that's super fair. It's just different from the type of AI that I'm talking about, and I would like people to understand that those are different. All right. So we know games needed AI, but it turns out AI needed games more. Can I like hide these? No? Okay. I mentioned how AI research was not taken very seriously, particularly neural networks, from the 1950s to like the 1980s or 90s. This is often called the AI winter. If you want to Google it, there's a good Wikipedia article about it. That's the term for it. We might be headed to another one. And we know in retrospect why, and the reason was there was so much hype and promise about AI in the 50s and 60s, and it just didn't work. Like it never lived up to the hype. And so people were like, I'm not funding your AI research. We're not going to hire AI scientists. We're not going to teach AI courses. It doesn't work. Let's just go back to graph search algorithms and we'll teach that. We know now that there are a couple of reasons why we had that winter. One was the lack of computational power that we have now. And two was the lack of training data, which we have much more of now. One of the types of machine learning we've mentioned is supervised learning. Supervised learning is a kind of learning where you're given an input, you make a guess, and you get immediate, complete feedback about how good that guess was. So for example, computer vision, which until 2012 was a very hard, unsolved problem, as represented by this XKCD comic. where it says, when a user takes a photo, the app should check whether they're in a national park. And the programmer says, that's easy, give me a few hours, just a GIS lookup. And check whether the photo is of a bird. And says, oh, well, I'll need a research team in 5 years. And it says, it's really hard to explain why some problems are difficult. What's funny is that this comic was published in 2014, 2 years after AlexNet, which we'll talk about in a minute. So this was no longer true at the time this comic was published. But this is that problem. Check to see whether the image is an image of a bird. What you see here are images from a data set called ImageNet that was a big part of the research lab led by a researcher named Fei Li at the University of Stanford. Her thesis was that the machine learning algorithms are fine. They're just missing training data. And so she spent a large amount of time, a decade I think, collecting images and applying labels to them and saving them in a machine-readable way, like tens of millions of images. And she started up this competition called the ImageNet contest, where she would publish 50 million of these labeled images and keep 10 million of these images secret. And she would say, in a year, whoever writes the program that most correctly identifies what's in the pictures of these 10 million held back secret images will get a cash prize. And so, do we have are these on the next slides? Yeah. So you can see how this went. This is this chart is the error rate, so what percentage of the images were incorrectly labeled by the winner of the ImageNet challenge each year. For the first 2 years, 2010 and 2011, this is about what the state of computer vision science was in those years, right? And that's about how good it had been for about a decade before that. Progress in computer vision was very slow, incremental at best, and people thought it was pretty fragile. Like if you took the techniques that worked on ImageNet and won these competitions and used them on another computer vision data set, they did not work as well. So they didn't generalize very well. Until 2012. It is hard to express how gigantic this improvement in 2012 was. So Usain Bolt, we're all familiar with this guy, very fast individual, more or less unbeatable at his height, right? Because he runs the 100-meter dash in like 9.87 seconds or something like that. And if you run it in 9.89, that's considered world class. And those 0.02 of a second difference make him like almost unbeatable. Nobody could match that. And so he's considered just mind-blowingly, like, you can see the matrix levels of like superhuman talent. Imagine if somebody showed up next year and ran it in 6.7 seconds. That is the mathematical equivalent of this increase in 2012. This came out of nowhere. Some researchers in Canada produced AlexNet. They took a neural network, and specifically what's called a convolutional neural network that does computations that kind of match the physical makeup of your eye cells, the way your eye processes images. They matched that in math, which people had done before. One of the things they did differently was they realized that the math of training a neural network is identical to the math, this is old news now, is identical to the math that computer graphics researchers use to render 2D and 3D images onto the screen. So we already have a GPU in our gaming rig. Can we just do the math on there? And you can, and it is billions of times faster. The way to think of a CPU on your machine is that you have a room full of 12 PhDs. Anything that you want done, somebody in that room knows how to do. A GPU is having a football field full of middle schoolers. So if you need a simple thing done many times, you're going to want the middle schoolers, not the PhDs. So if you want people to look at two sticks and tell you which one is bigger, and you have 10 billion sticks to compare, you want the middle schoolers, and that's what a GPU is. And people had done that before, but they realized that the value of this is that they could train their neural network, assess it, and iterate on it. So they could do experiments much faster than anybody had before. And as you might imagine, if you showed up and ran the 100-meter dash in 7 seconds, people would say, how are you training? And nobody would ever train a different way than that. That would be the only way that people trained now. And that's what happened with ImageNet. Every single year since then, it has been a convolutional network trained on a GPU that has won. As you can see on the image, we don't run the ImageNet contest anymore because the machine-learned models are better than the humans doing the labeling. If modern computer vision systems disagree with a human label, statistically it's more likely that the human is wrong than the computer vision model. So the problem of what is in this image is basically solved. It's like this is something that you can easily do. This is so solved, you can just download like a package in Python or Lua or C++ or whatever you're using to code your game in, and use it just like that. You don't have to know anything about how it works. You just give it like an RGB matrix that represents like an image, and it will tell you, or a tensor, I guess, and it will tell you what's in the image. And it's so efficient now that you can do that in just a few seconds. The very first model of this took several seconds to identify an image and do all the computation. It is not like that anymore. It is much faster. It can run on your phone. It can run on your watch if you have like a smart watch now. So ImageNet is no longer like the standard, but this is where it started. In 2012, when AlexNet demolished the ImageNet competition, everybody realized deep neural networks are back. They're a thing. We can do almost anything with them. There's all kinds of stuff that we could do. But what do you do after 2017? Like, we did everything we could with this data set. So what is next? Different companies realized that they had good labeled training sets. Yelp had a huge database of restaurant reviews with free text. So you can learn to judge sentiment from text, because this text is associated with like a thumbs up, and so you can machine learn that this text is like a good sentiment. Netflix had your reviews of which movies that you liked. There are a couple of like wine rating websites that realized you could associate which wines you like, and so you can predict what wines you're probably going to like. There's all kinds of stuff that people figured out, but within a couple of years, all those were exhausted. So there aren't any unused data sets anymore. There is no magic data set out there that has not been wrung completely dry of usefulness. People have used all the data sets. And the other thing is, for a lot of real-world practical problems, there are no data sets available. So if you want to machine learn how to fly a plane or how to drive a car or how to do surgery, there's no data sets available for those. But if you want to, because if you want to learn how to drive a car, you need to have some way to generate data for that. You can, if you want, put a neural network into a car, turn it loose on the streets of, I don't know, downtown DC, and then when it crashes, recover it, update, run the machine learning algorithm so it gets a little bit better, and do that again. That's obviously very slow. It's going to be expensive. You will kill children, so it's not a good way to do it. Can you think of a place that you could get a high-quality traffic and driving simulator that represents day-night cycles, traffic, vision, has a complete representation of the Los Angeles highway system? Yeah, Euro Truck Simulator. Yeah, great answer. So researchers turn to games to find a way to learn. We've talked about supervised learning, which is a kind of learning where, like I said, you get an input, you make a guess, and you get immediate and complete feedback about how good your guess is. The way that works with an image is you say, I'm 98% confident this is a cat. And if you're very highly confident and it's wrong, there is a 0.98 difference between the 0 that you should have been and the 0.98 that you were. And that wrongness you can use to propagate back through your network and update the weights of your network, and that's how it learns. The problem is that doesn't work for a video game, because if you make a move in a game of chess, what is the outcome of that move? The game is still going on. So you don't know if that's a good or a bad move until the game is over. You don't know whether you win or lose until the end of the game. And even then, you don't know if the move you made was good. And even if you do, you don't know if it was, you don't know how good it was. Was that the best move in the game? Was that just an okay but better than bad move? Is that the move that won you the game? Maybe it's a move that lost the other person the game and all of your moves were just kind of blah. The math for supervised learning, like those image computer vision problems, does not work here. Reinforcement learning solves this. These are called the temporal gap problems. There's a gap between when you do a thing and when you get feedback. And the credit assignment problem. Lots of things contribute to the outcome of a thing. So how do you know which thing is right? The way reinforcement learning works is the way that everybody learns. You have an environment that's in a certain state. You look at that state and you consult your policy, which we call PI. Your policy is just your strategy, like how you look at a state and decide what action to take. You take some action. The environment might give you back a reward, like if you jump on a Goomba in Mario, you get like 100 points, so you get some reward. And then the state changes, like that Goomba's not there anymore, so the state is different. And then you just do that over and over. So this is what reinforcement learning is, and this is the answer to how do you make NPCs interact better. If you have a little pet sheep and you slap it every time it does something you don't want it to, you can reinforcement learn it to learn what you don't want it to do, and it will do that less. Can it learn to play a game? The answer was no. Lots of researchers tried to fit machine learning into reinforcement learning, and they couldn't get it to work. It wasn't until 2014 when DeepMind, the company founded by Demis Hassabis, that black and white programmer that I mentioned before, his company full of very expensive researchers invented something called deep Q learning, which takes its name from Q learning, from reinforcement learning. And the idea is the problem with getting a machine to learn to play a game is that each state in the game is very, very, very similar to the state previous to it. One of the first things you learn in statistics is how correlated data can stop you from learning meaningful things about it. So the way deep Q learning works is you play a game, you record the action you took, the reward you got, the state you went to, the next action that you took, and then the result of the game at the end, store them all together, put them into a great big box, and then when it comes time to learn, you just draw a bunch of random states from different games that you played so that they're not serially correlated, and learn from that. This is a bit sci-fi because like what you're doing is you're storing robot memories. And the robot is learning from different things' memories. Have you ever watched Westworld where they talk about reveries? You ever watch Blade Runner where they're like, where are these random electric unicorn dreams coming from? It's the same kind of thing. So you can do this. And if we look at that, we can see an example from this was published in 2014, the same time as the Deep Q Learning paper. This is a game learning to play the Atari game Breakout. When it starts, it's just playing randomly, right? It clearly does not know how to play the game. If you let it learn for a couple of hours, now it plays like an expert. It knows what it's doing. This was trained with deep Q learning, and the only thing it knows is the score and the visual representation of the board. If you let it train for 4 hours, it figures out that if you get the ball above the bricks, that's the way that you score the real points. At this point, it's playing at a superhuman level. And at this point, it would do this every single time. This is not an accident. It would actively try to make that happen. So it's better than a human player at that point, using this deep Q learning technique. So that's how you code an AI. You don't. You let it learn. This is Garry Kasparov, famously being defeated by Deep Blue, which is a supercomputer in the early 90s. That was the first time that a pro had lost to a computer playing a game, and that Deep Blue was a supercomputer with a huge amount of computational power. Did all kinds of Monte Carlo tree searches and tree pruning to figure out what states in the chess game were right to follow up on. But it was hand-coded to play chess, and not just chess against Kasparov. They used every trick in the book to figure out how he played and code to run against it. In 2016, DeepMind, using their program AlphaGo, beat Lee Sedol, the world's best Go player, 4 games to 1. And they didn't code it. At this point, the way AlphaGo, the original system, worked was they learned from a bunch of recorded games of Go, and then after it got a little bit okay at the game, it played itself and learned from self-play. So it played billions of games of Go, more games than any human could ever possibly play. A few years later, they published Alpha Zero that didn't learn from human games at all. It started from nothing and learned strictly from self-play, and AlphaGo Zero is now much, much better than any human could ever be. The AlphaZero approach is generalizable. They published a chess version of AlphaZero that is 1,000 points stronger than Stockfish. If you're familiar with Stockfish, it's 1,000 points stronger than any human that's ever been. And AlphaGo Zero chess crushes it every single time. This also uses a huge amount of computational power, both to train the AI and to actually run it, but they didn't code it. So that's one of the other ways you can code an AI. You don't. You let it learn how to play, and that's how you can get it to learn. I asked you if you could think of a driving simulator. Where's my mouse here? This is a video from a researcher a few years ago who, it's got to be like way in the middle, right? This is him showing so if you just have a bunch of instances of Grand Theft Auto playing, you can get a pretty decent simulator for how to drive a car, and no children get run over, which I think is the correct number of children to get run over. Well, yeah. So and this Grand Theft Auto simulator this is Grand Theft Auto 5, right? Famously cost like $120 million to make. So much more money than any research organization could ever possibly even receive, much less justify spending on a simulator for a single research project to like help out learning a self-driving car. The reason this high-quality driving simulator exists, the reason why they were able to dump $120 million into producing this game is because we as gamers spent $6 billion on it on launch day. So this is available for researchers to use because we as gamers paid money to have it developed. So when I say AI in games is a two-way street, AI needed games, but games needed AI, and so AI needed games. This is what I'm talking about. Games drive AI now. Hello? Oh, I have the video still playing. I am very intelligent. A few years ago, the AlphaDog trials ran in 2020. This was a tournament where the best AI-controlled fighter pilot got to fly against the Air Force Top Gun instructors, the Air Force equivalent of Top Gun. And the AI-controlled jets smoked them every time. It's not a fair comparison because the AI pilots had information that the human pilots didn't, but it's like a stepping stone in like the path of research, right? And the way they tested this is in Ace Combat 6. They didn't use the Air Force simulators, they used a video game because that's what the researchers used to train their AI-controlled jets in. So how do we go from Pong, where the AI is like, move it up and down, maybe, and that's the extent of the AI logic, to this Monte Carlo tree search complexity that AlphaGo uses. So we talk about if-thens, that doesn't work. Tree search is okay, but there are problems. You can move on to machine learning techniques. Action and state value functions like Q-learning and learning policy functions, which we usually designate with a pi, are how you do that. So you have the game tree of tic-tac-toe over here, part of it at least, and you can do deep Q-learning on tic-tac-toe, just like we talked about. You can learn through self-play. In the lower left, you see this is called the Bellman equation. This is like kind of the core math of reinforcement learning. It looks big and scary, but it represents stuff that you already intuitively understand. This summation over, where's my mouse here? This summation over pi here, this pi is your strategy, and all a strategy is given a state S, what action are you going to take? And so you look at every possible action that you could take, find out what your probability is for taking that action, and then you look at what the probability is that you'll go to a given other state, get a given reward, and then multiply that times the reward that you get, plus the reward that you'll get for the rest of the game following that policy. So it simplifies to basically the reward you get for doing this plus the value of the next state that you go to. If you study sabermetrics like baseball statistics, you will be surprised to discover that a grand slam is actually worth 3.98 runs, not 4 runs, because if you hit a home run, you still have a full bag of bases, or you still have bases loaded, right? So you can keep scoring runs. So even though you score 4 runs on a grand slam, the state you go into is much, much worse than the state you just left. So sometimes the statistics work out a little funny, and you can use classical statistics to figure that out for baseball. It's much harder with video games, and you can use machine learning like this to do this. You can understand this math with, you don't even need linear algebra really, just the statistics 101, calculus 101, and that's it. And you can build up from there. You do need degrees if you want to be like a researcher because the math nowadays is much more complicated. There's a lot of stuff built onto this. But if you just want to understand what libraries you're using as a game developer, all you need to do is convince yourself that you kind of understand how it works so that when it does something wacky or when it starts behaving weird, you know what questions to ask and where to start. You might think to yourself, but how is that possible for, like, because you have to look at every single state, right? We just talked about how games have quadrillions of states. To express why this works, I'm going to propose a very simple game to you. The way this game works is the computer gives you a number between 1 and 1,000,000. I have 23 of the numbers selected here, and you give it a number back. And the game tells you whether you have selected the correct number or not. Well, if these are the correct numbers, and we know there's 1,000,000 of them, you would have to enumerate all 1,000,000 states and figure out what each of those are. It might be extra hard. What if they're non-deterministic? What if the computer selects from a distribution of numbers that are the correct number? You would have to learn that probability distribution too. It gets difficult quickly. So you'd have to learn all a million numbers, right? Well, actually, what if you discovered that if you took the number and plugged it as x into this equation, if you round that up to the nearest integer, you get the same numbers that you see here. So this is a little trick you can use to avoid storing a million different numbers. Actually, all you have to store is 3 numbers. You have to store the 0.004, the -0.2, and the 12. The trick is, how do you discover this equation? And the answer is machine learning. If you're going to model like a more complicated game, then obviously the equation will be much more complicated. But it's really not so different from this. It really is just y equals mx plus b with many more mx's and b's. So that's how we get to this. So games need AI, and they provide an environment. Research needs an environment, so they provide solutions. Devs use solutions to make games. Gamers pay for games and justify the creation of more games. So this is how, like, it's a closed loop now with AI research. All right, second JoJo pose. Yeah! I'm 42 now. That's not as easy as it used to be. All right, we have a couple more questions, but I think I have 5 minutes of time left. I don't know if the next panel has shown up or not, but I think it's more important to talk about how my predictions in 2022 about how I thought AI was going to change were wrong, and how and why I think they were wrong. If we have time, if like the other panel doesn't show up or something, we'll do more questions. Are you sure?
Yeah, there's a 30-minute break.
Well, yeah, but you're supposed to clear out 30 minutes ahead of time so they can set it up, but whatever, we'll see. So anyway, how was I wrong? I thought the way that machine learning was going to find its way into games was that game developers and game studios were going to look at the difficult problem of coding an AI and use machine learning as a solution to this difficult problem. But I was wrong. What game developers are doing now are using machine learning to generate art assets. Very little machine learning is being used as AI. There is some, and we'll talk about in a second why there's not as much of that happening. But what I thought would happen is they would take a hard problem and use this difficult solution to solve that hard problem. What actually happened, the thing is that art assets are straightforward to generate. It's not easy. Like, being an artist is like a real difficult thing. You have to train to do it. It's not something you just like feel like doing. You have to practice. There's a lot of like expensive, difficult skills involved in it. But we know how to make art assets. You hire artists, you hire a program manager, you pay your artists, and they make the art. Like, that's a solved problem. But it's expensive. So what these game design studios, particularly large ones that have lots of zeros after their like game development costs, is they realize that it's better to use a cheap solution to replace an expensive solution than it is to use an effective solution to solve a hard problem. So there actually isn't much financial incentive to use difficult machine learning to make better AI, because we can just cheat. That's cheap. Like, we have lots of ways to solve this solution. But art assets are expensive. They take time. I remember when The Division came out, it was pretty famous that they had like 300 coders and somewhere around 4,000 artists. Most of the cost in modern AAA games is artists, because game engines are very good, so you don't need to recode them. But if you want your game to look and feel different, you need to create all new art assets, and that's expensive every time. So why not just fire all of the artists and pay pennies for a machine to generate your art assets for you? So the results are in game financing. So why was I wrong? Game AI is difficult, but it's inexpensive. Like we said, you can just write some cheats that make it feel like it's good. One of the other problems is that reinforcement learned models don't generalize well. The AI that you train to play Planetary Annihilation Titans, which does use reinforcement learning to drive its like AI opponents, you can't just lift that and put it into I don't know, Tekken 7 or whatever Tekken we're up to now. It's a stupid game anyway. Don't play Tekken. And it can be tough to use in real time. If you have this gigantic billion parameter model and you give it a game state, it might take 30 seconds to compute what it wants to do. And if you're playing a fighting game that runs at 60 frames per second, that doesn't work. So it's difficult to do that. Asset creation is straightforward but expensive, and generative models, particularly image generation models, do generalize well. We don't really have any time. I was going to go explain why generative models do generalize well, but we'll skip over that. So here's my prediction for from 2026. I don't think the AI-generated assets will stop. The financial incentives for large game studios particularly are too great, and I even don't blame indie developers to it. If you're like a programmer, it's intimidating to realize that artists are expensive, and if you don't know that a bunch of people are going to buy your game, that's coming out of your pocket, and it's probably not coming back. So the pressures are too great. Maybe gamers don't care. Some gamers do. Like if you go on itch.io, there's a tag that asserts that no AI assets were used in their game, and there's lots of games in there. So there's an interest in human-generated games that are not like AI-generated. But you're just counting on the devs to promise that they aren't. I don't know if you guys saw the recent controversy with Clair Obscur. There was a little bit of AI-generated content that was used in development as a placeholder, but it made it through QA into the final game. I believed that was accidental because they replaced it immediately. They were like, we didn't mean to do this. It's really just a placeholder that we use in development. This is a mistake. But it didn't matter. They lost all their Game of the Year awards, and people assigned them to different other games. But how do you know that that's the only AI-generated content in there? Like, AI-generated content is more and more becoming indistinguishable, especially to a non-expert, from like human-generated art. So you just have to take their word for it. We have limited means of verification. I'm not going to plug this too hard. I have invented and patented this technology that I call Miles, after the scientist from Terminator 2 who decides to give up all the gigantic profits that he could make to destroy AI instead of chasing the profits. And the way it works is you sign like the content of your game, your file or whatever, and you have this trust network where if you can draw a path of trust from you to whoever made that art asset, you can verify that there's like a human out there who made that art. I won't bore you with the technical details. My vision for this is if you build this into Steam, you can imagine that there's like a verify human-generated content function, and it goes through, checks all the files, and says we can verify 77% of this game is human-generated or whatever. It does work. I've started a nonprofit to stand this up. If you have any interest in like participating or contributing or in some way, if you just want to follow it, you can send me an email. That's my email address right there. So this might not be the only solution that people come up with for this, but there has to be some verification solution because right now we're just taking the word of the people who publish it, and we've seen that their incentives are not good. Their incentives do not incentivize them to be honest about this. They incentivize them to get away with it more effectively. So that's what I think my predictions are. All right, so I think we're out of time. If we do have some other time and the other panel is not here, we can answer some questions. But if we don't, you can come, hang out with me out in the hall and ask whatever questions that you want. Thanks so much for coming to the talk. I really appreciate your questions. I'm sorry we didn't get to all of them.